So I'm very glad to be here, and I would like to thank the organizers for the very kind invitation. So as you can see, the topic of my talk will be on self-supervised learning for vision. So I should say here that although most of the techniques that I will talk about will relate to visual data, actually many of the methods that I will describe and present are actually applicable to many other domains, which is actually one of the reasons that I chose to talk about this topic, because I assume that the audience in this summer school will be from many different domains. So you can think of this as a kind of short tutorial for those who are new to these SSL, self-supervised learning methods. So here is a brief outline of the talk. I will start by motivating why we need to use self-supervised learning. I will explain what do we mean by self-supervised learning. And then I will try to provide a flavor of different SSL approaches that are used in practice today. Okay. So we're in the age of deep learning, and what works very well in this age is basically the supervised learning setting. So that means that, let's say you want to create an image classifier that discriminates between cats and dogs. Well, what you do is the following. You collect a very large set of images of cats and dogs, you annotate them with the correct label, and then you take a neural network, and for each image you make minor modifications to the weights using HGD in order for the network to make a correct prediction for the given image. So to make correct prediction for the given image. And so if you do that many, many times and for many annotated images, at the end you're going to get a very robust classifier, which is very, very powerful. Okay? So this setting works extremely well. This supervised setting works extremely well. It's basically been the powerhouse of many of the developments over the last years. Now, this setting, however, has some disadvantages, has some problems. Okay? And the first one has to do with the fact that we need to collect a large number of examples. And actually, it's not the fact that we need to collect the examples. The problem is that we need to annotate them. Okay? And in many cases, this annotation is very, very time-consuming and costly. For instance, even if you have to provide just a single label for a given image, if you have to do this for millions of images, this can be expensive. Let alone if you want to provide more detailed information, like in the case of semantic segmentation, where you want to provide pixel-level information, this can be even more challenging. Okay? And in fact, there can be application areas or domains where this is even more difficult, like in the case of medical imaging, where in order to do annotation, you need to be a doctor. You need to be a qualified human expert to provide the annotation. So this is even more challenging. And even if the cost of the annotation was not a big problem, let's assume that, there can be several occasions where basically you don't have many examples, labeled examples, by default. This is known as the long-tail distribution problem. So you can have training sets where you have a small number of classes with a very large number of examples, and you have a long tail of a large number of classes with a small number of annotated examples. So in this case, we don't have labels for these long tail classes. But even if we somehow were able to address this problem, there is a deeper and more fundamental issue in this case, which relates to the fact that this supervised setting assumes that we're using a fixed data set, a fixed set of classes, fixed set of data, and so on and so forth. Okay? And so what we're doing in this case, we're learning a representation which is optimized for this specific data set. Okay? But actually, this is not what we really want in practice. In practice, we want to have a representation that can be easily adapted to new classes, to new data. Okay? This is the real challenge. Okay? And this is exactly why this supervised learning setting is in deep contrast with how humans learn. Okay? So when a human is born, nobody is giving him 1 million annotated examples. So this is a dog, this is a cat. No. We learn by simply observing the world around us. So basically, we learn by observing unlabeled data. Okay? And so the real question is, how can we exploit this unlabeled data? In fact, this question has been essentially the holy grail of machine learning for many, many years, how to exploit unlabeled data. Okay? Because if you can do that, there are plenty of unlabeled data available online. So you can have images, video, text. Okay? How can we exploit all this stuff? And this is exactly the motivation and idea behind SSL, self-supervised learning. Okay? How to exploit this data. And in fact, this idea, when combined with another idea, which is transformers, which is a very flexible architecture, neural network architecture with the right inductive biases, which is very efficient to train. If you combine these two ideas together, this has led to very important breakthroughs over the last a couple of years. Okay, what is self-supervised learning? Let's try to look at this question. So remember, we want to solve somehow the unsupervised learning problem, okay? But what works very well is the supervised learning setting, okay? So what essentially we will try to do is the following. We will try to reduce the unsupervised learning problem into a supervised learning one, essentially. And how we're going to do that? We're going to do it by defining an auxiliary task, an auxiliary objective. Typically, we call this a pretext task, okay? And basically, this pretext task has to satisfy two important conditions. So the first condition is that you need to be able to generate labels for these pretext tasks automatically without human intervention. And the second condition, which is the more difficult one, this auxiliary task, this pretext task, needs to relate somehow to the task that you actually care about. Okay? And I will give examples in a minute of what I mean. So what happens in this case is basically, you take your input signal, you apply some pre-processing, and the kind of pre-processing depends on the pretext task or the auxiliary task. At the same time, you know what is the correct labels, what is the correct output based on the pre-processing. Okay? And now you're in the supervised setting. So now you can have your network, and you can train it on as many data as you like. And hopefully, if your pretext task makes sense, then hopefully some useful behavior is going to emerge. This is the idea. So just to give a very simple example, so let's say you have your signal, which is an image. You apply some noise. This is a pre-processing in this case. And your goal now is to reconstruct the input. The input is known in advance. You don't need any annotation. So you have input, target. Now you can use, let's say, an encoder-decoder neural network. And notice that in this case, we don't care actually about the output of the decoder. The useful behavior emerges at the output of the encoder. This is the representation that we care about in this case. And this is very common in SSL. Typically, you use a network, and you are actually using an intermediate representation of this network later on. So this is just a very toy example. I will provide many examples later. So basically, one can think of SSL as a kind of the platypus of machine learning, because platypus is an animal that looks like a mixture of many different animals. And similarly, you can think of SSL as a mixture of unsupervised and supervised learning. So basically, as I said, we're doing unsupervised learning by using supervised learning approaches. And so typically, the training pipeline in this case proceeds in two stages, basically. So the most important stage is stage one, the pre-training stage. So in this case, you use an encoder, a backbone. We call it F. And then you define a classifier for your pretext task. This is your pre-training. Here you use just unlabeled data. We don't actually care about this stuff here later on. Okay? So when, at stage two, when we want to adapt to a new problem, to a new task, what we do is throw away this classifier, and we just keep the encoder. Okay? And the simplest thing we can do is we can keep the encoder fixed and just have a linear classifier on top, which is trained on the new task. This is called linear probing. If you want to be more fancy to get better performance, you can actually do fine-tuning of the encoder as well, and again have a nonlinear classifier on top. You can do in context learning, you can do all sorts of things. Okay? But the important stuff takes place here, stage one. Okay? So this is the idea in this case. Actually, I'll skip this in the interest of time. So all this sounds very nice, but is it actually very, very useful, okay, in practice? So if I had to give this presentation a couple of years back, I would need to show plots, argue this is useful, why not? I mean, nowadays I can simply say GPT and everybody will understand what I mean. Okay? But to make a long story short, essentially if you use these SSL approaches, essentially when you want to adapt your representation to a new task, what you gain is basically you gain efficiency. Okay? Both in terms of samples, this is the plot on the right, but also in terms of number of epochs, number of iterations you need to train, to adapt. These are the plots on the left. Okay, so this is the main advantage. Okay, so as you can imagine, there are many different SSL approaches. And here you can see a taxonomy of these type of approaches based on a NeurIPS tutorial that took place a couple of years back. I won't have time to cover all of them. I'll basically try to do the following. I'll try to provide a short tour of some representative approaches, starting from, let's say, the early methods, trying also to show how these approaches evolved over time, which I also find it quite interesting. Okay, so in the early, let's say, days of SSL, what happened is that everybody was trying to be very creative. So everybody was trying to propose a new pretext task. Okay? So in this case, many of these tasks in the early days were related to the so-called transformation prediction problem. Okay? Like for instance, in 2007, we proposed the pretext task of predicting image rotations. Okay? So in this case, I give you this image, which has been rotated, and I ask you to tell me, okay, what is the rotation of this image? Okay, I'm sure all of you can infer this information. Okay, this is easy. But what about this image? If I give you this random noise image, can you infer the rotation? This is impossible in practice. Okay? The difference between these two examples is what? In this case, you can infer the rotation because what? Because you can recognize the content of the image. So you can recognize there is a human, you can recognize the head of the human, you can recognize the body of the human, and because of gravity, we usually take images in a certain orientation. The head should be above the body, so we can infer the rotation. Right? So the crucial thing here is that basically to solve this pretext task, you need to recognize the content, and this is the idea in this case. It helps a lot if you can recognize the content. If you don't, it's very difficult to do a systematically good prediction. So for instance, in this case, how pre-training works, you take your image with no label, you apply a random rotation of 90 degrees, multiple of 90 degrees, you get this image, and then you train a neural network to predict the rotation. So basically, it's a classification problem with 4 classes in this case. Very easy to train. And in fact, this worked very, very, very well, extremely well. Actually, we were surprised when we first implemented this. In fact, at that time, what everybody was doing was fully supervised ImageNet pre-training. So everybody was using ImageNet, which is a large data set of annotated images. They were pre-training on this, using the labels, and then they were adapting the representation to a new task. Okay? And this gave a good, decent performance. This is one of the first works that showed basically that we can significantly close the gap by doing this SSL pre-training. Okay? So in this case, we're again using the ImageNet, but we're not using the labels. We're just using these pretext tasks. And still we can get a performance which is very close to to the performance of fully supervised pre-training. If you don't do any pre-training in this case, because in your new task you have not enough data, which is this row here, you are going to overfit, so you're going to get very bad performance. Or just another example. This is the context prediction task. So in this case, the task goes as follows. I give you 2 patches from an image, and I ask you to tell me what is the relative position of these 2 patches in the image. Again, the idea is similar. To be able to recognize the relative position of these 2 patches, you need to recognize the content. Otherwise, it's a very difficult task. So in this case, you need to recognize, okay, this is the top of the bus, this is the bottom of the bus, so, probably this is the correct relative position. Okay, so in this case, how pre-training works, you randomly sample a patch from your image, then you randomly sample one of the 8 neighboring patches. So you get these 2 patches here, let's say the blue and the yellow. You pass them through the same network, so these 2 networks share weights, okay? And then you train on top of classifier to predict the correct relative position. Again, it's a classification problem with 8 possible classes because you have 8 possible neighboring positions. Again, notice the following. We don't actually care about the classifier. This is too specific for the pre-training task. What we care about is the representation from the network here. This is what we will use afterwards. Again, some intermediate representation. Actually, a kind of more difficult, challenging version of the same task is the so-called jigsaw puzzle pre-training. In this case, you take a random crop from an image, you divide it into 3 by 3 9 patches, you randomly shuffle them, and then you train a network to predict the correct permutation, to basically do the unshuffling. Okay, again, random crop, you divide it to 3 by 3 patches, you get this sequence, you permute, each patch is processed independently from the same network, so all of these networks share weights as before. And then you train a classifier on top who is supposed to predict the correct permutation. Another example, colorization. You take a grayscale image, actually a color image, you remove the color, and then you ask a network to predict it. Again, to solve it, you need to be able to, it helps if you can recognize the content. And in fact, if you apply this approach, this coloring pre-training approach to video, so in this case, let's say you have a video, you keep the color from the first frame, and you remove the colors from all remaining frames of the video. Okay? And then you ask the network, okay, tell me what are the colors for all these frames. Okay? The emergent behavior that results from this pre-training is basically tracking. Okay? Because the most efficient way to learn to color in this case is basically by tracking the objects through the video. Now, I want to make a note here regarding, let's say, the colorization approach. One disadvantage was basically that we were training a network that was only using the grayscale information. So it was throwing away the color, right? Which is suboptimal because we want to work, let's say, with color images. So one way to address this is basically by using a so-called split brain autoencoder approach, in which case you do the following. You take your image, you have the grayscale part, you have the color channels part, and then you train a pair of networks. So F1 is going to predict the color from grayscale, and F2 is going to do the reverse. And so now you have a pair of networks that basically process your whole input. Okay? And basically you can do this not just for images, you can do for any type of data X where you have multiple channels. Or you can basically divide your channels into, let's say, X1 and X2. F1 should predict X2 from X1, and F2 is the opposite. Okay? And again, you have a network that basically exploits all of your data. all over your channels. Okay, these are some examples from some early approaches. As you can see, there are various different pretext tasks. But after some point, after some time, people started, asking the question, is there a more, let's say, a principle or a more generic approach to try to tackle this SSL problem in the sense that we would like to apply it to many different, possibly, domains, okay? And one class of methods that resulted in this case was the so-called contrastive-based SSL approaches. And basically, in this case, the initial formulation was basically as an instance classification problem. So there was this exemplar covenants paper, which did the following. So you have a training set of images, which can have many images. So you randomly pick one of these images, and you apply a random augmentation. Actually, not random augmentation, an augmentation which is random, but which doesn't alter the semantic meaning of your image. Let's say you change a little bit the colors, you apply some geometric transformation like cropping, and so you get a new image, like this one image here. And now you ask the following question. Can you tell me where this image came from? I mean, meaning, what was the training sample it came from? Instance classification problem. And the idea in this case is the following. The representation that we're going to learn in this case will be invariant to these augmentations that don't change the semantic meaning of our data. Okay, which is something that we would like to have. So in this case, you have your image, your signal, you apply your augmentation, and then you train a network to predict the ID of the correct training sample it came from. It's again a classification problem with cross-entropy standard classification problem. Of course, there is a practical problem in this case, which is the following. This classification problem is a very large-scale one in the sense that you have many classes, as many as the number of training samples. So let's say you have an ImageNet which has 1 million images. You're going to have 1 million classes. So this is not very practical to solve. Okay? So the way to overcome this is, instead of formulating this as a classification problem, we're going to formulate it as a metric learning or as a contrastive problem. Okay? So essentially we're saying that, if we have a pair of augmented images, which are two different views of the same image, we want this pair to be close to each other, have high similarity, and be very far, have low similarity with random other images, basically. Okay, so now what happens is the following. You take your data, your image, X, you apply two random perturbations, augmentations, and then you train an encoder and a projector network G, so that in the latent space you maximize agreement between augmentations of the same image and maximize disagreement between different images, basically, this contrastive task. So in practice, you have your mini batch, you take each image in your mini batch, you apply two random augmentations, you pass them through the encoder, through the projection head, which is typically an MLP, and then you basically have a contrastive loss that enforces similar the augmentations of the same image to be attracted, and different images to be far away from each other, basically. Okay? And the contrastive loss is something similar as this thing here. So in the numerator, you have the similarity between augmented views of the same image. In the denominator, you have similarity between all other images, basically. And this very simple idea, which is quite generic, works surprisingly well. And basically, you can very easily scale this approach. Scale meaning you can increase the number of parameters of your model because you don't need labels. You can use unlabeled data. And if you scale it far enough, you can actually surpass supervised performance. And in fact, the gains are even greater if you just use a very small fraction of labeled data. In this case, the gap is even larger. You get even bigger benefits. I will say two remarks here. So the first one is basically has to do with the augmentations. This is really important. You need to choose your augmentations correctly depending on your data. And it's very important to use a wide variety of augmentations and compose them. Okay, this is very important. They did a systematic study about this. The other thing that I want to stress is that in this case, for these methods to work well, you actually need to use large mini batches, large batch sizes. Why is that? Because remember, the number of negatives that you have depends on the size of your mini batch. And so because this is a contrastive method, you contrast against negatives, you need to have a lot of negatives in your mini batch, which is a problem because this means you need to have a lot of memory, it's costly, I mean, it's not desirable. Okay? There are some approaches, contrastive approaches, that try to overcome this by maintaining, let's say, a queue or a memory bank of negatives, of hard negatives, and they keep reusing it. Okay? This is known as the MOCO approach. Okay? But still, it's not very optimal. Okay? And so this problem, the idea of trying to get rid of having to use a lot of negatives in the contrastive-based method has led to another class of approaches, SSL approaches, which are based on the regression or self-distillation paradigm. So the idea in this case is basically the following. Instead of having a contrastive formulation, we're going to formulate the problem as a regression one. So basically we have our data, our image. We apply two different augmentations. And basically what we want is the following. We want to be able to predict the representation of the second view from the representation of the top view, of the first one. So it's a regression problem. So you no longer need negatives to contrast. So in this case, you have an encoder, as before. You also need a predictor, in this case, for one of the branches. And basically, the goal of the predictor is to predict the representation of the bottom branch, of the bottom view. And the interesting thing, the surprising thing, this was really surprising when this BioL approach was first proposed, is that you can actually bootstrap the whole process. So you start randomly, and despite the fact that you start randomly, because of the inductive bias that you are using a neural network here, the representation that you get here at the output is slightly better compared to the representation that you get at the input, the raw pixel representation. So you have a slightly better representation here, and now the top branch, by trying to predict this representation, it also improves. So after training a little bit, you get something better here. You take this, you copy it here, and you keep repeating, basically. This is the idea of bootstrapping in this case. Actually, we don't do this copying because this is very inefficient. What we actually do is we're using an exponential moving average approach. So again, we have two branches, the online or the student branch, and the target or the teacher branch. And basically, during training, we're training these, the online network, and the teacher is always an exponential moving average of the student. This is self-distillation, teacher and student. Okay. And again, this works surprisingly well. Again, you can scale the model very easily because you can use unlabeled data, and you can get very good performance, and you don't need to use any negatives in case, just a prediction, a regression problem, which is a great benefit. This is very similar, another approach which is very similar is the Dino approach. Okay. Actually, this is even simpler because they actually managed to get rid of the predictor. They are not using a predictor in this case. They are doing some other tricks. I won't go into details, but it's a regression, self-distillation approach which doesn't use a predictor. It's even simpler. And actually, at this point in time, people started using these transformer architectures for visual data, the visual transformers. And actually, if you train this, if you use this Dino approach for pre-training, The interesting behavior that emerges in this case is semantic segmentation. So basically, if you look at the attention heads of the transformer, in this case, you see that the representation that you learn focuses on semantic objects or object parts. So here you can see some images and some attention maps, and you can see that they focus on the objects in the image. And all of these without any labels. This is just label data. It was really interesting when this idea was proposed. Now, in this context, what we proposed was something that was based on this visual, visual word representation. So we took inspiration from NLP in this case. So what I mean by visual words, I mean the following. Let's say we have some pre-trained controller theme, which can be, let's say, some self-supervised model. You can use it to give it as an image and get a map of features. And you can cluster them, you can do this for many images, you can cluster them, and you can think of each cluster as a kind of a visual word. Right? So it's a visualization of visual words, and basically they will call them mid or high-level subsets in this case. And now you can use as a representation of the whole image a histogram of these visual words, basically, so these clusters. But basically we use this idea in this context of you apply an augmentation, and then you train a network to predict the bag of visual words of the original image, using as input just the augmented image. Again, you force the network to focus on mid-high level content by use of these visual words representation. And actually, it turns out that you don't need a pre-trained encoder fee. You can actually, again, bootstrap the whole process. So you start with some encoder fee, and as the training progresses, this encoder improves and gets better and better, meaning that you get better visual words as the training progresses, better visual concepts. Okay? And this works very, very, very well. This is the OBO approach. And in terms of results, I mean, at the time of application of this, it was giving very good results, and compared to state-of-the-art, let's say, contrastive or self-distillation or regression approaches. A third very popular paradigm for SSL is the so-called self-prediction or masking methods. Again, the idea is very simple. You take your image, you take your signal, you hide a certain part of it, and then you ask the network, this is your pretext task in this case, you ask the network, okay, now try to reconstruct the missing signal. And a lot of approaches in this area took inspiration from NLP, from text, okay, where you have a sentence, you hide certain parts of the certain words, and you ask the network to predict the missing words. A very famous example in this case is the so-called BERT model, which uses an encoder-only architecture neural network, which is basically a transformer, to solve this missing word prediction task, basically. And you can actually do the same thing for images. Okay? The only difference is the following. For images, you don't have this discrete set of words, of symbols, these tokens. So additionally, you need to train a tokenizer, which is basically an encoder-decoder reconstruction network that will basically take your image and will give you as an output a set of discrete visual token IDs, basically. Okay? So once you have this tokenizer, which is done in advance and independently, then you can follow the same recipe. So you take your image, you break it into patches, you mask some of these patches, so you end up with a sequence of masked and visible patches. And then you use, again, an encoder-only transformer architecture, where the goal now is to predict the visual token IDs that correspond to the masked patches, basically. Actually, this is one possible way of going about implementing this idea, a more efficient implementation of this idea, more optimal implementation of this idea for vision, for visual data, is to use a so-called masked autoencoder. So in this case, instead of having just a single encoder-only architecture, you are breaking your model into encoder and decoder, basically. Okay? And the encoder is only processing the visible patches, and the role of the decoder is to reconstruct the missing patches. Now, what's the benefit from this? The benefit, one of the benefits, is the fact that the encoder is only has to process the visible patches. And in images, for visual data, it pays off if you hide a lot of patches, because there's a lot of redundancy in images. Okay? That means that you have a very short input here, so training in this case is much more efficient. Okay, so once you have trained a network like this, you can test it, let's say, on new images to see what kind of reconstructions it gives. So you can see some examples here. On the left is the original image, and you can see some reconstructions for different masking ratios. As you can see, then the network is doing a pretty reasonable job of reconstruction. Now, as I said, for images, especially for images, this is not for NLP. For text, it's not the same. It's different. But for images, the most effective approach is basically to use high masking ratios. You need to hide a lot of patches to get something meaningful as a representation. So it's not uncommon to have a masking ratio between, let's say, around 80%. Okay, this is very common. Now, there are a lot of approaches based on this idea. Okay? And most of them basically choose the patches to hide, to mask, in a random fashion. Okay, so one of the questions that we tried to explore recently was, okay, is there a better way, a more clever way to go about this, the selection of what to hide in an image? Okay. And the interesting thing is that it turns out that you can actually use the attention of the transformer that you are training during pre-training to decide what patches to hide. This is often very useful. And what is very useful in this case is basically it pays off if you try to hide those patches that are most highly attended by the network, basically. The intuition is that in this case, you make the problem harder and you force the network to learn to focus on new features each time. Okay, so you see here you can see an example. So this is your image. Let's say this is the attention map during training. And so you can think of this as, as a kind of probability map based on which we sample the patches to hide during pre-training. Okay? Of course, this is a dynamic process. As the training progresses, this attention mask improves and gets better. And the main benefit by doing so, by using this more clever way of selecting what to hide from your data, you gain efficiency again. You accelerate the pre-training process, which is very, very important. One last comment is basically the following. So if you take these, these masking or self-prediction approach to the extreme, meaning you hide all of your signal, okay? This is going to lead to the so-called generative-based approaches. So in this case, your pretext task is what? You are training a network to generate your data, your images, your whatever, from scratch. See GPT, for instance. Okay? And one common way to do this is by using autoregressive models. And again, you can use either convolutional architectures for images. This was done in the early days. Nowadays, everybody is using transformers. But anyway, it's the same idea. Okay, I will close with two remarks. So the first remark has to do with the following. Although I presented various approaches, various different paradigms, I might give you the false impression that these are all different from each other. Okay? They are not compatible. This is not true. You can actually combine ideas from many different approaches. Like in one of our recent works, MOCA, we basically proposed the SSL approach that combines self-prediction with self distillation, okay, which also helps to have better performance. So this is one remark. And the second remark relates to something which is often, I mean, not just in SSL, it's a general remark for neural networks. Neural networks are generally very lazy modules. They always try to find the easiest way to solve the problem they are given. And so that means that if you are not careful how you are defining your SSL problem, your pretext task, sometimes you are going to get something which is undesirable. You're going to get representations which are not useful. Because the network, instead of learning something useful, it is learning shortcut features. Okay? Like for instance, let's say this, remember I described this context prediction task, where you need to predict the relative position between two patches. If you are not careful and you don't introduce some gap between the patches, what the network is going to learn is what? Continuity features. Low-level features not very useful for semantic information. Okay? How do we resolve this? We are going to introduce some gap between the patches so as to force the network to learn to concentrate on semantic information. Or to give another example, you can have a network that takes as input a single patch from an image, nothing else, just a single patch, and is able to predict where this patch is located inside the image without having seen the image. You might say, okay, how is this possible? Okay. Well, this can happen if you are using a data set where there are chromatic aberration artifacts, because in the case the artifacts, the appearance of the artifacts depends on the location of the image. So the network is utilizing these chromatic aberration artifacts to solve the task in this case. Okay, so if you do something like this, training is wonderful, loss is going down, and you think that you have learned something useful, and at the end what you have learned is how to recognize chromatic aberration artifacts. Okay? So be very careful, for your data preprocessing, how you define your pretext task. This can be very important. Okay, I'll stop here, and if you have any questions, I would be glad to answer.
Okay, well, thank you very much for the presentation and for leaving ample time for questions. So, are there any questions from the audience? Maybe I can ask one to get us started. You mentioned the rotations that were in units of 90 degrees, but many images may have random amount of rotation. Can that be implemented? How hard is to implement something like this?
So you mean to define a pretext task where you have not just multiples of 90, but
any angle?
Yeah, we actually tried this. Doesn't improve a lot the performance. And I don't know if you can guess the reason, but the main reason is that these 90-degree rotations are very, very simple to implement, and they don't introduce any artifacts. Let's say if you do a 45 degrees rotation of your image, you get these aliasing artifacts, and the network is going to learn these artifacts to solve the problem in this case. So you don't gain much. So this is the reason why we are using just 90 degrees. Turns out this very simple selection is very effective as well.
Okay. Let's see. More questions? Yes, please.
Hi. I have a question about the attention-guided masking. We're doing something, we want to do something similar in 3D structure modeling, on self-supervised 3D structure modeling. And one problem that we have is that it's somewhat very sensitive to the normalization that we apply before any kind of softmax application. So either it's batch normalization or layer normalization. And I'm wondering whether these attention maps can sometimes misinform any masking strategy, depending on whether on how you transform your attention weights. Did you have any kind of these problems in your case, or what kind of normalization did you use?
So actually what we did, I mean, perhaps I can go back. Let's say here. So if you just, let's say, use these attention mask as probability, let's say one possible way to tackle this problem is basically, okay, pick the top, let's say 10% of your attention weights, and you get something like this. In our case, this worked. I mean, you have to play a little bit with, what is the top percent, okay? But what worked even better is what we call providing some additional hints, okay? So we are masking based on highly attended tokens, but we're also giving some hints because otherwise it might be, too difficult for the problem to be solved. This worked better in our case.
But how do you know these hints?
You just select, again, based on these weights, you select a small number of these highly attended weights and you present them to the network. These are the hints. Okay. So you hide most of the highly attended, but you just give a small percentage of the top, let's say, attention weights.
Thanks.
Okay, more questions? Yes, please. Right there, yes.
Thank you for the presentation. Might be slightly irrelevant, but when you were comparing for the rotating image paradigm, when you were comparing the supervised and unsupervised methods, when you were comparing the unsupervised and the supervised frameworks, you mentioned you were only comparing them based on accuracy. But what would be the comparison based on the number of parameters between the two?
Yeah, that's a correct observation. If you have a fully supervised model with the same number of parameters as an unsupervised model, and for the fully supervised model, you're using, all the labels, nothing is going to beat that. This is my first slides, basically. Supervised learning is the best approach if you can afford it. The problem is that oftentimes you don't have these labels. This is what I'm trying to say. And if you don't need labels, what I'm suggesting is that you can scale your model. Because if you try to scale your model without increasing the number of labels, what can happen is you can get overfitting.
Thank you.
Yeah, actually, if I'm not mistaken, providing labels is a very expensive.
Yes, exactly. This is the problem.
So
Yes, exactly.
Yeah.
When I say you can't afford, I mean you have to pay.
It's a very expensive. Okay, more questions? Yes, please.
Thank you, Nikos, for the great presentation. I see that that different kinds of techniques for exploring, the space of your data are being applied. For instance, you're rotating, you're masking, you're augmenting, and so on and so forth. Is there any technique that applies noise, for instance, in order to apply, diffusion and so on?
Sorry, can you repeat? I didn't hear.
Is there any technique that you can apply noise, in this case?
You can apply noise, yes.
Yes, and apply diffusion techniques.
Yes. Actually, this is what you just mentioned, is the idea behind diffusion models. They do exactly that. So this toy example that I presented at the beginning, where it was basically a denoising autoencoder. You apply noise and then you try to reconstruct. This is the basic idea behind diffusion models, which works. So I would say that basically in this case, I would classify this diffusion model as a kind of generative-based SSL methods. You try to generate your data from scratch by using this. By introducing this noise, basically.
Okay. Any more questions? I don't see one. Oh, there it is. There's one. Yeah. Please go ahead. Or can we get a microphone over there?
Thank you. Just a very general question from someone who is not very accustomed to SSL. Do you think there are tasks that are better suited to SSL and others that are not? And is there some kind of characteristic that perhaps allows SSL to shine more in some applications rather than others? Or is it general enough a paradigm to apply everywhere?
Yeah. Again, if I had to give this, if I had to respond a couple of years back, I would need to argue a lot about this. Again, I will say GPT. Yeah, I mean, these methods seem to work very well. I mean, again, if you have a task where you cannot afford having a lot of data, because this is when deep learning really works. You need to have a lot of data somehow. Okay? If you can't have a lot of data, then this pre-training approach, where you're basically preparing your network to learn useful things about your task, typically helps. Of course, there is the challenge that the pre-training problem has to relate to somehow to your task. Okay. But as I explained, there are some general principles, some general approach like masking, self-distillation, contrastive approaches. These are generic approaches. I mean, all of the things that I described, I mean, I could completely omit the image part and still describe them. Okay, these are just signals. Okay, so I think they are generally applicable. So yeah.
Thank you.
One more question at the front here.
That was very nice and clear presentation for even the ones that were not working in the field. In your the last one of your slides, you suggested this model as a composite hybrid of all the others. So you can parameterize, no, not this one. This one, yeah. So I guess this says that depending on your task, I can parameterize the use of the different mechanism.
Exactly.
And train the parameters on how much to rely on one or the other technique. So, I mean, could you give us a little bit more detail on how to do that? Because this is very interesting.
Yeah, I mean, I don't have time to go into the full details here because it's a bit complicated, but just the general idea. So here, we have an image here again, and we're basically combining, let's say, the masking approach and the self-distillation approach. Actually, the visual bag of words approach. Okay? So we have our image. Again, we mask some patches, as in the masking case. But at the same time, we're taking, at the same image, and we're creating two different augmentations, two different views. Okay? And now the task is the following. We have to, the network is trained to do what? Filling the missing part here, but also do some kind of self-distillation, predicting the bag of visual words based on these representations here. So it's a kind of a mixture of these two approaches. And again, I'm not saying that this is how everybody should do this or implement this. My main message is that you can combine approaches. This is the most important point that I want to convey, basically.
Okay. Any more questions? We still have a few minutes, so maybe I'd like to take advantage of this and ask another question myself, if I may. So you mentioned something very interesting, that neural networks are lazy, you call them.
Yeah, very lazy.
And in fact, we've come across this many times in our own work, trying to solve differential equations using neural networks, where the network very quickly converges to the zero solution, which is the trivial one and the very lazy one. So could you elaborate a little bit? How do you avoid falling into this kind of trap?
Yeah, how do you avoid this? There's no recipe, unfortunately. Yeah, this is an open problem. Actually, I guess this is. This is bad, but at the same time, this is what gives the neural networks the power to solve problems, because they try to exploit the easy features first, and probably, the simplest explanations are typically, the most generalizable sometimes. So this is a good thing in general, But of course, you have to be careful because if something is too simple or it does not relate to your problem, it can be detrimental. But there's no recipe. At least I don't know a recipe to avoid this. You can do all sorts of tricks, regularization, stuff like that, but it's an open problem.
Okay. Thank you. Well, maybe you can thank the speaker again.